Okay, today we are going to continue our lecture on unconstrained optimization problems with more than one choice variable. So the objective functions you will see have at least two arguments in them, two variables. And there's a decision maker out there who can decide, gets to choose. That's the word choice. The choice variable, that's where this comes from. There's really a person thinking about what should I choose? And I'm not just choosing one thing, I'm choosing multiple things. And it becomes a more complicated optimization problem because of that. So here's some more examples. I gave you two examples last class, but this one will be a third. See, that was example 2 right there, as you can recall, maybe from last class. How about example 3? It's a two-product profit maximization problem. And this might be more common than you realize, that there could be firms out there who produce multiple products, and the products are substitutes for each other. You know, Apple makes an iPad and a laptop, and those are actually, some people use both. Some people buy both a laptop and an iPad. Some people just buy one and use it for both purposes. I'm sure Microsoft and other companies do the same. But just think of all the multiple examples of a company that indeed is just trying to maximize their profit. They're trying to choose a quantity and price to generate as much profit as they can. But they have to keep in mind the fact that if you make too much of one product, it's going to substitute away some of your demand for your other products. And that's, you know, it's not necessarily a good thing to just saturate the market with both products. When I say saturate, I mean extract as much profit as possible from both markets. What you need to do is do it jointly. One maximization problem for both products. And that's what I want to talk about. Let's look at this. You can hopefully see this formula for pi. Pi is profit, often in economics. It's not 3.14159. It actually just means profit. The reason the Greek letter pi is used instead of the English letter P is because P is reserved for price. So that's why we use profit or pi. What have I written here? What I've written here is simply the profit function after it's been simplified. So I could have started from scratch here and said profit equals revenue minus cost. Revenue equals price times quantity for each good. So rather than starting from the basic fundamentals, I kind of went straight to the profit function, and I can explain it, I think. The first term, well, Q1 is the quantity of good 1 produced. Then this term here in parentheses is the price that the monopolist, I'm kind of assuming this is like a pseudo monopolist, somebody who has some market power. The reason I'm assuming they have some market power, or at least, is because Q1 appears in this parentheses. In other words, they're not a price taker. They have some control over what the price is in this market. And the highest price they could possibly charge is given by this 10 minus Q1 minus Q2 over 4. So Q1 is, that's this, you know, the law of demand says that price is downward sloping with respect to quantity. That's why this is negative. 10 minus Q1 is the downward sloping nature of demand. But minus Q2 over 4, that comes from the fact that these goods are substitutes, meaning that if I produce too much of good 2, Q2, I will actually be losing some of my demand, at least some of the price that I can charge for, because people are less willing to pay that higher price for good 1. So Q2 over 4 is something which sort of reduces a bit the revenue I get from product 1. Okay, so this first term is the revenue from product 1. Okay, from product 2, of course, I produce Q2 of it. And this here is the highest price I can charge for product 2. Just like before, the 20 minus Q2 part is the downward sloping demand curve. Of course, the more quantity I want to sell, the lower the price I have to charge. But then once again, there is this substitution term here that says the amount I can charge for good two is smaller as I produce more of good one. Like if I'm making a bunch of laptops and I've already flooded the market with a bunch of iPads, then people are willing to pay less for the laptops because they may already own an iPad, something like that. Okay. That's the intuition for this formula, but really you don't need to, you can solve it just using math. And that's what I would like to do today because I think we have some time. This is just one more example of an unconstrained maximization problem. Oh, sorry, what do we have? 12:49. Let's make sure I'm like, 1:15, something like that. I'll make the quiz available. Okay. Let's see what we do. Oops. Darn, I don't have a screen with that's very blank for me just to write on. Can somebody tell me what to do here? Find the profit maximizing quantities. This is a maximization problem. This is an optimization problem where the two choice variables are what? Q1 and Q2, right? It's not X and Y. That's okay. It's Q1 and Q2. This whole formula, this whole function is the thing I want to maximize. Was somebody saying something?
Yeah, I was just saying the first order condition would be to take the derivative with respect to Q1.
Very good.
That's the first order condition 1, and the second one would be take the partial derivative with respect to Q2.
Very good. So, and that's of the whole formula here for pi.
Mm-hmm.
That's correct. So what we want is this sort of d pi dq1. I wonder if we could do this just by looking at it. And that is, we could use the product rule here. We don't have to, but let's just use the product rule. I'll show you how it works even when you don't need to use it. Okay, so the product rule is I'll take the derivative of the first term and leave the second unchanged. So that is 10. By the way, the derivative of Q1 is just 1. I'm not even going to write it. 10 minus Q1 minus Q2 over 4. Okay, that's the first term. Then we leave the first term unchanged and take the derivative of the second. The derivative of the second is actually -1 with respect to Q1. See, there's a -1. So I'll subtract Q1 from that. And how about from over here? There's no Q1 here, so you don't have to use the product rule this time, but there will be a Q2 multiplied by -Q1 over 4. The derivative of that with respect to Q1 should be -Q2 over 4, correct? Because you treat Q2 as a constant. Does everyone see how I got that?
So you multiply the Q2 throughout?
Yeah. What I did, I'll just tell you what was going on in my mind is I'm hunting for Q1s, right? I'm taking the derivative with respect to Q1. So I'm looking here and I'm saying, where are there any Q1s? I see one here, I see one here, I see one here. And I just need to make sure I've accounted for all of those when I take the derivative. And for here, I use the product rule because they're two different things being multiplied together. But for here, I didn't need to use the product rule because I'm not too worried about Q2. It's just it's treated like a constant. Yes, Jordan, or no, Jordan, Jonathan, or Colin, I think it's Colin that asked this question. Yeah, you can just pretend like the Q2 is being distributed to each term, but I didn't even need to worry about this term or this term. I only need to worry about this final term because that's where the Q1 is, and it's minus Q2 times Q1 over 4. The derivative of that is Q2 over 4. Understand where I got this?
Yeah.
But you know what, guys? If you write this as your first order condition, I will give you partial credit, but I will not give you full credit. This will be something I will be a stickler on.
Equals 0?
You got to say equals 0, because if you don't say equals 0, it's not a condition. It's just a statement. It's a statement about a differentiation. Okay. A condition is something which is either true or not true, and you want to write that as equal to 0. Okay, And then we might also do it with Q2. By the way, how can we simplify this? I know I see a 10. I might use my eraser here to cheat a little bit and say minus Q1 becomes minus 2Q1. Can I put a little 2 there? That's really floppy, but I can tell. And minus Q2 over 4 minus Q2 over 4, that will become minus Q2 over 2. And because a fourth plus a fourth is a half. And even this equals 0, you could sort of, you know what, let's do maybe an arrow instead and say this implies, thus the arrow. Oops, I forgot the equals 0. I erased the equals 0. I'll leave that for now. It implies that if I move the Q2 over 2 to this side and multiply through by 2, I can solve for Q2 in terms of Q1. Isn't that what you would do? You would try to solve this for one variable in terms of the other would be the natural thing to do. Because I'm looking ahead. You're going to want to solve this system of equations. And you know, maybe methodologically you would prefer to first write out the first order conditions and then solve the first order conditions. Yeah, that's probably a little bit of a nicer, cleaner way to do it. But just right now, maybe because I'm conserving space, I'm simplifying this equation to say Q2 equals, once I move it to the right side and multiply by 2, I'll get 20 minus 4 Q1, I believe. This is not a solution by any means. It's really just one equation that we derived from this first order condition. This is FOC1. Alexandria Ocasio-Cortez. That's AOC. FOC2 is going to be similar. Of course, that's d pi dq1, dq2, I mean, just because it's kind of like pretty clear that Q1 is the first choice variable and Q2 is the second. It's by the sort of the same arguments here, it's going to be what, negative Q1 over 4, and then plus 20 minus Q2. You guys can check me on this, minus Q1 over 4. Now there's this term where I take the derivative of the inside, which is -1, and multiply it by just this term, which is a negative minus Q2. By the way, you would get this exact same answer if you first multiplied through the Q2s. Said, okay, this is 20 Q2 minus Q2 squared minus Q2 times Q1 over 4. You would get the exact same thing. Just this Q2 and this Q2 would have been already combined to be 2Q2. And let's think about what that would be. Once again, I see a negative Q1 over 4 on both sides. Not on both sides, but I forgot the equal 0. I just told you not to forget the equal 0, but I forgot the equal 0. Okay, let's call 20 minus Q2. I'm sorry, it's 2Q2, isn't it? 20 minus 2Q2 equals a negative Q1 over 4. Negative Q1 over 4 becomes negative Q1 over 2. Move to the other side, it becomes Q1 over 2. I didn't need to move it to the other side, but I did. Okay, so this is, you're free to use whatever sort of algebra simplification you like. I think I'm pretty flexible in this class about how you solve something. I sort of think that might be kind of your preference, your taste. I like to solve it this way. You like to solve it that way. I think if you're just using algebra accurately, you can get the right answer. And I don't care so much how you solve it. But now we have these two equations that can be combined. I might plug in what I have here for Q2 and get 20 minus 2 times this quantity equals Q1 over 2. And that's one way to solve for Q1, right? I'm just running out of space. So what I'm going to do is delete what I've written and show you the slides, which has it written much more nicely. But actually, before I do that, does anybody have any questions how I got here? How I got these, is there some way to just like highlight, you know, this is a formula Q2 and Q1. Here's another formula with Q2 and Q1. You see how I got that, those two? They come from the first order conditions of this optimization problem. And using them, we can solve for Q1 and Q2. And I'm going to do that on the next slide. Okay? If there's no questions, I assume no one wants to see any more about this, and I'll go on. Your all drawings. Okay. So here it is, written out perhaps a little cleaner. Yeah, I'm noticing that these D's should be curly D's. It's not a big deal. Indicate that that's a partial derivative, not a total derivative. That's just a notational thing. But here are the first order conditions. And here they are solved in pretty much the same way that I solved them before. Negative Q1 over 2 plus 20 minus 2. Remember, I had this whole thing. I had this whole thing solved for Q2. I plugged that in, equals 0. Now, what sort of Q1s do I have? I have a negative Q1 over 2 here, but I have a positive 8 Q1 here. And I have a positive 20 here, and I have a negative 40 here. Together, those become negative 20. And I can move that 20 to the other side to get this equation. That's how I got this. It comes straight from what I just had on the screen, written with my mouse, but now it's written using, I believe, PowerPoint. This is a PowerPoint slide, which is only available, I'm using on PDF for some reason, but it's a PowerPoint slide. What do I have time-wise? 101. Okay, so then you just solve this for Q1. Easy. 15 over 2 Q1 equals 20, therefore Q1 equals this, 2.67. This is a, you might say, man, what a small number. Oh yeah, what if it's in millions, right? I didn't tell you the units of this function. This is a general point I'm making about economics, is that when we do our problems, especially they're just examples that illustrate something, we don't really care about the size of the numbers, the magnitude of the numbers. That's not the point. The point is to demonstrate some of the nuance of profit maximization when there's, you know, two products that are substitutes, something like that. And even if you did say, well, I care about the numbers themselves and the magnitudes, well, this could be measured in millions. I didn't say what the units of Q1 were. It could be units of iPads in millions of iPads produced in a year, right? So this Apple saying, okay, we need to produce 2 million iPads this year. And this is millions of MacBook Pros, or MacBook some kind produced, whatever. And that would make the problem seem more important if it's measured in millions rather than ones. But at least now you see, here's an example of a more of an applied example of using this method of optimization. It's an optimization problem. Hopefully you can do problems like this. I can give you any problem like this with multiple choice variables and find the first order conditions. You can solve them simultaneously to get a solution. You could then check that it is indeed a solution. How would you do that? Second order conditions. Right? Let's do that. I think I have a slide of second order conditions. I do. Does somebody want to say what they would be here? We need to look at the Hessian matrix, right? Here's written out the first derivative with respect to Q1. Here's the first derivative with respect to Q2. from there, we can get the second order partial derivatives pretty easily, I think. Might be worthwhile to annotate this. What is like, how would I write this now? I wouldn't write it as fxx, would I? I'm quizzing you right now on notation. What would be the notation for the second order partial derivatives here?
Would be
That-
Q1, Q1.
Say that again. F.
Q1, Q1.
Okay, you could, yeah, you could, or you could use pi. I've already labeled this function as pi instead of f. You could use pi, but you know what? You could use f too. I would know what you mean if you use f. But yeah, if you, I'll do this here. Pi instead of f. Q1, Q1. That's hard to write for me. I almost have to do lowercase. Oh, never mind. This is pretty awful. But it's the derivative of this with respect to Q1, which I think you can tell right away what it is. -2. Bam. And then there's a cross partial, pi Q1, Q2, and then there's the other second order derivative Q2, Q2. Sorry, guys. I mean, I'm just go by what I'm saying, not by what I'm writing. I realize what I'm writing is not very legible. What I'm saying here is that the cross partial derivative pi with respect to Q1 and then Q2, I would look at this formula and say, where's the Q2s in it? They're here. It's -1/2. Because -1/4 plus -1/4 is -1/2. And then if I wanted to get pi Q2, Q2, I would look down here and say, where's there a Q2? It's here. That's also -2. So the Hessian matrix here is constant. The Hessian matrix doesn't have any Q's in it. All of the Q's vanished. What we have left is, I think I'm gonna, by the way, everyone see how we got this? How we got these numbers here? The numbers are -2, -1/2, and -2.
Yeah.
Also, I didn't bother to do pi Q2, Q1. It's always the same. It's always also going to be -1/2. Did somebody say something? Kai. I'm sorry, did you say something? No? Okay. I'm going slow here. I apologize, but what the heck? I want you guys to do well. I want you guys to do well in this quiz. I think you can. I don't think I'm asking you anything you can't do. I have faith in you guys. Let's, what happened to my, oh no, I can't even delete this stuff. Clear drawings. Nope. Here we go. Sorry. Done. So the second order conditions is this Hessian matrix right here. -2, -1/2, -1/2, -2. You should be aware that there could have been Q's in there, right? If there was something a little bit more complicated for this formula for pi, like if there was a logarithm in there, or if there was something raised to a fractional power like q to the 1/2, something like that, then you would almost assuredly have some of the variables here, Q1 or Q2, within the Hessian matrix, and that would be fine. You should not freak out if that happens. All you do is take what you found as a potential solution, that's Q1, that's Q2, and you would plug that into the Hessian matrix. Turns out you don't have to do that here. What is the second order?
Before you find the determinant?
Pardon. Say that again, Colin. I'll listen to you better this time.
Would you plug in the values for Q1 and Q2 before you take the determinant?
Yes. I mean, you know what? You don't have to, but I would.
Okay.
You know why?
Okay.
Because
Yeah,
I think
I guess you could write it out too, and then plug in, and then
yeah, you could. The answer to your question is it's up to you. The better answer is that's what I would do.
Okay.
Because then you just have numbers that you're multiplying together rather than terms, and you're less likely, I think. Correct me if I'm wrong. I think you're less likely to make a mistake when you're multiplying numbers than when you're multiplying a formula.
Yeah, I agree.
Kai got kicked out. Kai, did you get kicked out? I'm sorry. I don't know how that happened. It wasn't me. To quote the great Shaggy, it wasn't me.
Sorry, I got kicked out. My
Yeah.
internet.
So now well, let's finish off this problem and say, how can we tell for sure this is a maximum? What is it again? Somebody tell me. I'll do it in green here because it's like a check.
It needs to be positive.
The determinant,
Yes.
but it's not just the determinant, right? There's two things we have to check.
Oh, if it's a max, fxx has to be less
Yeah,
than 0.
so it's not really fxx in this case, but I know what you mean.
Yeah.
It's pi q1. And the
Oh,
reason is in this example, the objective function is pi, and the first choice variable is q1. So
and it's
You know,
always
if
that
you-
spot, correct? Like it would never be pi q2. Like it's always the fxx.
maybe you forgot this, but I did mention this in one of my lectures that it actually doesn't matter. You could look at this one, or you could have looked at this one, and those are totally equivalent. And the reason, that seems a little like this is like befuddling. Like, what if one's negative and the other's positive? Then doesn't it matter? And it is possible that one is negative and the other is positive. So I'm not saying that. I just want to be clear here. I'm not saying that when one is negative, the other will always be negative, or when one's positive, the other will always be positive. I'm not saying that. What I'm saying is that in order for this condition to hold, in order for the second order condition to hold, it must be the case that they both have the same sign. Therefore, I only need to check one of them. And in order to realize that, you have to realize that what's going on here with this other diagonal, those two numbers are always the same. So when you multiply them together, it's going to be like a squared number, which is always positive. And if I'm going to subtract a positive number and the answer is still positive, I must have started with a positive number. And the only way I could have started with a positive number is if these two things have the same sign. Is that weird? That's the logic. If that logic doesn't totally make sense, or if I said 5 sentences there and you didn't flow from one sentence to the other sentences, I think don't worry about this. This isn't a big deal. The point is, you can check either one by convention, by default. Usually you just check the top left. That's what I do when I'm doing one like this. By the way, if I have time today, which I don't think I will, I would tell you a little bit about what happens when it's 3 by 3. When the Hessian matrix is 3 by 3, it changes again. It's not just that I check the top left and the determinant and I'm done. I actually need to look at the top left. The top left is still there. Then I need to look at what happens with the top 2 by 2, right? Not the top, the sort of, I probably don't need to be even telling you this right before a quiz, you don't care. But if this were 3 by 3 and there were other numbers here, here, and here, then I would do another thing where I just look at the top left submatrix there and make sure it has the important properties that it has, for exactly the same reason that I don't need to check all of them, because it's sort of implied within the condition that if it's true for that one, I don't have to check the others. And then finally, I would look at the determinant of the whole thing. I'm not going to have you guys do that just because it's, it's just more you'd have to learn that. You could learn that later if you ever needed it, but not for this class. Okay, for this class, you should know how to do it for 2 variables for these types of problems when there's 2 choice variables. Clear drawings. So you see now why this problem is done. This problem is done because I don't know if I actually made the point that I wanted to make. This is positive. Not positive, it's negative. How did I say that? It's negative. -2 is negative, so that's good. And then, check. Determinant H is positive because -2 times -2 minus -1/2 times -1/2 is 15/4, and that's positive. So that's it, we're done. It satisfies the second order conditions. I'm not really saying whether it's necessary or for sufficient. I think technically these are the sufficient second order conditions for a local maximum. And if you wanted to convince yourself that, hey, wait a second, could there be something else that's even higher than this local maximum, some kind of a global maximum? You should answer, your answer to that should be no, because the Hessian is enough to show that this is always a concave function, at least, right? So if you wanted to go the full mile and say, we have found the global maximum of this profit function here, pi. We found the global maximum. We know that because the sufficient second order condition for a local max was met, check, check. And we can go even further and say it's a global max because the function is concave because the Hessian satisfied these same properties. Meaning that it satisfies the properties for all Q, not just for the one we plugged in, which we didn't even need to plug it in, right? If we had to plug it in here, we could say, okay, it's satisfied for that point. But then if we wanted to say, is it concave? We need to show that it's concave for all points, for all Q1 and all Q2. That's the difference. I think I'm about done with this explanation here. Hope you guys, well, no, I'll let you ask questions. Anybody have any questions? I guess there's a lot of terms. There's a lot of terms to be thrown around here. Objective functions, choice variables, first order conditions, second order conditions, Hessian matrix, necessary and sufficient, local and global. I think the good thing is that each of these terms has a meaning which corresponds to English. You know, if you're an English speaker and you've used these words before, they pretty much mean the same thing as they do when you're speaking about math. Hopefully that helps. Does anybody have any questions? I'm gonna clear and stop sharing. And I think I want to make the quiz available now. Quiz 4. I will switch over to Blackboard and do that. And then during the quiz, I'll probably mute myself, but I'll stick around. If you have any questions, one of the questions in the quiz has a math problem, an optimization problem. I think it's a maximization problem, and I used the Blackboard math font. And to me, it looks good on my screen. If for some reason it doesn't appear the proper way, because sometimes computers will compile is the word. They will compile this equation in some way, like, wait, I can't even see that. It's not meant to be confusing. If it's confusing, just ask me, and I will hopefully in words be able to explain what the problem is. And really there's just this one optimization problem, and then I'll ask you several questions about that one problem. Okay, there's two multiple choice at the beginning, and then there is one optimization problem with multiple parts to it. And that's the whole quiz. All I need to do now is make it available. Edit test options. I do think I want to make it timed. And once you start, you have to finish. I'll give you a lot of time though. How about, I said 30, but I'll be generous and give you 35. How about that? That's a lot of time, isn't it? For this. You want even more time? I don't even care. 40 minutes. The problem is I'll have another class that started, so you won't be with me the whole 40 minutes, but you'll have the time to you'll have the time to take the quiz. Once again, I think I said this about the due date, that I will put a due date on it, but if there's any reason, especially with the recent events on the campus of VCU, you want to wait a little bit before taking the quiz, just let me know.